So the mass extinctions have had effects on us, lots of effects. One creature gets through, thank goodness. This is us too. This is in the lowest Triassic, a little creature called Thrinaxodon. You can see this is a little skull. Here's a old-fashioned apparatus called a fountain pen, no longer in existence, self-extinct for scale. And we have in it a great big eye socket in through here. Here's its nose, here's its little teeth. It's about the size of a robin egg, and that is you folks and me, that's us. That species gets through, it survives this extinction, otherwise there are no mammals at all. But it gets through, but a whole lot more reptiles get through and they take over, and they evolve into dinosaurs, and that was it, age of dinosaurs, because of the Permian extinction. That's why there were dinosaurs. We can look in the Karoo Desert, the red line is that bad extinction. We can see all these series of creatures going out, but now the question becomes, could this have been an impact? And the answer is no, it wasn't an impact. Here's one of the science diagrams that we put out, and the bottom line here, the takeaway is these two dotted lines. At the Cretaceous Tertiary, you've got a line in the sand. Here we have a zone probably 50,000 years in length where things are going extinct, other things are evolving. There's a succession of short-term extinctions. Why did this happen? It happened because of volcanism. It happened because one of the greatest extrusions of basalt on the planet at the end of the Permian occurs in Siberia. We call this the Siberian Traps. Volcanism produces carbon dioxide that goes in the atmosphere. The world warmed by 10 degrees centigrade over this 50,000 years. 10 degrees centigrade changes a world and kills a lot of stuff. Warm planets produce hydrogen sulfide. We've got a hydrogen sulfide heated world, and it happened not just at the Permian, but other times as well. So here's a view from my friend Alexis Rockman of what's happening at the end of the Permian. Here's all our poor mammal-like reptiles. Guys that could burrow did a little bit better. Our little Thrinaxodon was a burrower. And then what you don't see in this picture running around are these stem dinosaurs eating up all the dead stuff. So how many were impact? And only one of them is impact. I'll finish here with the Triassic extinction, the one after the Permian. Again, UW Crew's been working on this. Beautiful place. This is the Queen Charlotte's. And this place in Nevada are both 200 million years in age. And once again, we get evidence of one of these 50,000-year extinctions. We have evidence of sudden volcanism. We have evidence of sudden global warming, and from various types of biomarkers, we recognize the ocean's filled with hydrogen sulfide. Some of it bubbles out. So why did this happen? Why do we get these short-term periods? It's the volcanism. It's the CO2. When a world gets warm, the poles heat much faster than do the equators. The equatorial region is already about as hot as it can be, but right now we've got ice on both poles. If you warmed Antarctica and warmed the Arctic, why are there ocean currents and wind? Simply because we have a warm and cold on this planet. If you make the poles as warm as the equator, there's no reason to have any wind at all, and you won't. Ocean currents, they stop. And when oceans stop and wind stops, the oceans go anoxic. They become stagnant. They're like nasty ponds. Hydrogen sulfide producing bacteria take over, and it finally escapes into the air. These are called greenhouse extinctions. We have 10 episodes of this, big ones and little ones. All you need to do is put a lot of carbon dioxide in the atmosphere. Wait a minute, this sounds familiar. So we see other records here, and these are isotope records. Isotopes is looking at the amount of carbon in organisms. There's a couple different types. You've heard of carbon-14, but these are carbon-13 and carbon-12. These become proxies for extinction and productivity. And that big swing to the left here under that red line, this is the world that has suddenly gone extinct, but then it goes back and gets nice again, and then it goes again. We're finding a series of extinctions. They are exactly equivalent to the times when these basalt flows maximize. You've got flood basalts occurring for 50,000 years, and then it stops, and the world goes back to nice again, and then another one comes. These are a succession of extinctions. They're not a line in the sand that an asteroid gives you. So the bottom line finally is that number 4 there is the only big impact extinction. And instead, if we look over the last 250 million years, we find these enormous swings of isotopes that happen when the flood basalts happen. We've got a big one here, we've got one here, we've got one here. We also, turns out, have a small one here in India. It's starting to swing right now. It swings when you start killing off productivity. The amount of oxygen in the atmosphere has been switching too, and I simply throw this slide up because it's so startling to me. This is our new view of the number of creatures through time. So here we are 500 million years ago, here's that big rise, and then things go up and down a little bit, then a big up, down, and then we go to the modern day. On the top is the amount of oxygen in our atmosphere over that same period of time. That's brand new. We haven't recognized that right now we're at 21%, that we had times going as low as 15%. We had times going all the way down to 12%. Those are the times when we shut down circulation. The times of low oxygen happen when we reduce circulation, when we have these flood basalts. Look at how there's a correlation between times of high oxygen and times of high abundance. So the oxygen there, the highest oxygen of all time, showed through here, drops down. I mean, these are just one-to-one. This is almost like science fiction. And it's all related to carbon dioxide. Every time we hit high carbon dioxide, we lost the ice caps. So let's look at a little more relevant sense of ice caps today and what some of the relevance to our world might be. Global sea level now is expected to rise, if we're lucky, 4 feet by 2100. Now, 3 feet of that is already built into the system. The ocean has warmed, it's got heat in it. The thermal expansion, when you warm water, the molecules spread out a little bit further. There's 3 feet of rise going to happen if nothing else in the world happens. If we can shut off every bit of CO2 in the atmosphere right now, it's still going to go up 3 feet. So let's look what happens if we make it, say, 5 feet in Bangladesh. And 5 feet in Bangladesh is that you affect 15% of the population, 16% of the land, but when I'm talking about 15% of the population, I'm saying 15% of the population get flooded out. But what you don't see here is the fact that salt water goes sideways through soil really fast. And crops can't grow in soil that has salt put in it. So what's really going to happen here is that Bangladesh, which can feed itself right now, won't be able to feed itself with a 5-foot sea level rise. And we're going to have 4 feet by 2100. So we're looking at 112 million people that's expected to be 150 million by that time that can't feed themselves. So where are they going to go? Because people are going to go to feed their kids. Well, they're going to go into India. Do you think the Indians are going to let that happen? No. This is the problem. This is why our security agencies are pretty worried about global warming. Because if you want the cause of human conflict, make it so you can't feed your kids, and that next country has places where you can. Mass human migrations on enormous scales are a possibility if we continue to cause sea level to rise. What is going on to ocean heat content? Because this is the important part. Ocean heat content is really going to affect sea level rise. And sea level rise, by the way, is the single #1 problem of global warming. Nothing else matters in a sense, because sea level rise affects crops. It's staggering to understand how much crop is at sea level or the first few meters above it. Every delta in the world, deltas are enormous productive places. In Southeast Asia, most of the rice comes from sea levels from the ocean to about 5 feet. The Niger, the Ganges, the Brahmaputra. You've got all these things, the Mekong, these giant deltas are areas where fresh water floods and you grow your rice right at sea level. You'll lose every bit of it. 4-foot sea level rise, we could lose 25% of world crops. It's going to rise because carbon dioxide levels keep going like this. This is faster than any time we've ever seen in the past, including those extinctions caused by flood basalts. So we're going up at 2%, 2 parts per million, per year. We are now at 390. We're going to be up to 400 pretty soon. And this is, again, human caused. We are seeing right now the effect of this warming. It happens more at the poles than it does at the equator. Here we've got Greenland, and new studies of Greenland show the warming. And what is it warming? It's warming the ice. Only 2 things matter for sea level rise, Greenland and Antarctica. Nothing else matters, because these are the great continental ice sheets. So if we melt all the ice on Greenland, sea level goes up 20 to 30 feet. If we melt all the ice in Antarctica, it goes up 200 feet.
Permafrost thaws. The organic matter in the permafrost thaws as well and begins to decay. The microorganisms start to eat it. If there's no oxygen, the microorganisms make methane. If there's oxygen, the microorganisms make carbon dioxide. Permafrost. Right here. Frozen dirt.
We found, as far as the organic matter coming out of this hill slope, is that it's much more bioavailable, meaning it's yummier for the microbes that are decomposing it. Sites like this, where the permafrost is releasing organic matter, act as accelerators. They speed up the process of human-caused climate change.
It's very much like the canary in the coal mine. If you're likely to see anything related to climate change, it will happen in the Arctic. There have been changes in the Arctic in the permafrost in terms of the temperature over time, not only in the shallow layers near the surface, but at 10, 20, and 50-meter depths, you're seeing changes that are even more rapid. That indicates that not only is there heating near the surface, but that this heat is being transported to depth. As the Earth's climate system goes from the relatively stable conditions that it has been, begins to transform into a new state.
The contribution of carbon, of organic matter being released from the permafrost region might amplify human impacts by up to 30%. So we put out a certain amount of carbon each year, around 10 petagrams, 10 gigatons of carbon each year. The permafrost system may respond by contributing up to 3 gigatons of carbon. So it's a large amplification of what we're doing. It feeds back onto our impacts. It's important to realize that the scale and rate of change that we're talking about now is several degrees, 2 to 5 degrees in just 100 years. So this is much faster than has happened in the last 50 million years. We're talking about unprecedented climate change and a very rapid, abrupt response from this ecosystem.
All of the models predict that the climate change will happen first in the Arctic. The climate change is predicted to be largest in the Arctic, especially over land. We're talking about forecasts where the surface land temperature might change by up to 10 degrees centigrade, which is approximately 18 degrees Fahrenheit over the next century. That's much, much different than what people talk about for global average surface temperature change.
So the mass extinctions have had effects on us, lots of effects. One creature gets through, thank goodness. This is us too. This is in the lowest Triassic, a little creature called Thrinaxodon. You can see this is a little skull. Here's a old-fashioned apparatus extinct. Other things are evolving. There's a succession of short-term extinctions. Why did this happen? It happened because of volcanism. It happened because one of the greatest extrusions of basalt on the planet at the end of the Permian occurs in Siberia. We call this the Siberian traps. Volcanism produces carbon dioxide. This had been an impact, and the answer is no, it wasn't an impact. Here's one of the science diagrams that we put out, and the bottom line here, the takeaway is these 2 dotted lines. At the Cretaceous Tertiary, you've got a line in the sand. Here we have a zone probably 50,000 years in length where things are going, called a fountain pen, no longer in existence, self-extinct for scale, and we have in it a great big eye socket in through here. Here's its nose. Here's its little teeth. It's about the size of a robin egg, and that is you folks and me. That's us. That species gets through. It survives this extinction. Otherwise, there are no mammals at all. But it gets through, but a whole lot more reptiles get through, and they take over, and they evolve into dinosaurs, and that was it, age of dinosaurs, because of the Permian extinction. That's why there were dinosaurs. We can look in the Karoo Desert. The red line is that bad extinction. We can see all these series of creatures going out, going out. But now the question becomes,